All right, we're going to continue on to our notes. We've just done the slope, interpreting the y-intercept. Now we're going to talk about this other thing about the scatter plots so that we can describe them. Remember how we described the distribution? Well, we're going to get into describing the scatter plot. All right, so it will not be done with our socks, but we'll see what it is with next. Here we go. So first of all, we want to talk about the correlation between these two items. And so a correlation is that measure of how these two quantitative variables are related. Okay, and we're going to actually later have a number value that will tell us how connected these two variables are to each other. So here's a perfect positive correlation. And of course, you can see the positive ones are going up from left to right. Well, that is because as the x variable increases, as the x value increases, then the y value is also getting higher. Okay, you know that. How about the negative ones? So we've got weak negative, strong negative, and a perfect negative. And so that is because as the x value increases, the y value decreases. Notice here in the middle, this is no linear correlation, okay? No, that doesn't actually look like any type of correlation to me. So next, moving on. So those are important to think about how as one item increases, the other is increasing. I've seen AP questions where they ask you to describe the relationship in the context of the problem. And so you had to say, well, as your height is increasing, then your shoe size is increasing or that kind of thing. All right. Now, next, we want to talk about the equation of the line that is going through those values. So that's this thing called a least squares regression line. We'll refer to it as the LSRL. You know it as that line of best fit. Okay. Later in a different lesson, we'll talk about why we are calling it this thing called a least squares regression line. But it roughly puts half of your data above it and half of the data below it. It's kind of the average of the data. All right, next. So if things are strongly correlated, then the data is close to the least squares regression line. Close, not closely, is close to the least squares regression line. It's closely clustered around that LSRL. And it's a good model to make a close prediction. You feel okay with that prediction you are making. But if we have a weak correlation, then those data pieces are far away from that prediction line. Therefore, it's a poor model. We don't feel like we have a good prediction. We don't feel confident in the value that we are predicting it to be because it's quite a bit off from the actual value. That prediction line would be quite a bit off. All right. So now we're going to talk about this thing, this new measurement, which remember that you were able to get on your calculator when you did your stat calc lin reg and you had the diagnostics on. Okay. And so then that gave us that R and R squared. So the first one that we're going to talk about is the R. And these names of these items are very close together. There's the R is called correlation coefficient, and R squared is coefficient of determination. See, I even have to try and scramble my brain to keep those straight. Therefore, I have a song to help you remember that the R is represented by the correlation coefficient. So we'll talk about its values here in a minute. So I don't have that video up, but I'll play that here for you in just a minute. The correlation remember that funky music? Play that funky music, white boy. Okay, so we got the correlation coefficient represented by the R. Correlation coefficient. The variable that you use to represent it is the R. Okay, so the correlation coefficient is our R. If we always remember that, then we'll know that that other vocabulary of coefficient of determination, which goes to Frosty the Snowman song, that is r squared. Okay, so here we go. Correlation coefficient represented by the R. So here's some numerical values to our perfect, strong, weak, and so on. R, if it's positive, the perfect relationship is a positive 1. That means you can tell me an X and I will tell you what the Y is. It's perfect correlation. Perfect negative is, again, negative 1. No correlation, no linear correlation is an R value of 0. Correlation coefficient of 0. Now, take a look at these other numbers. They are decimals. So an R value is between negative 1 and positive 1. The closer you get to 1, positive 1, the stronger the positive correlation. The closer to 0, the weaker the correlation. Now, over here on the negative side, look, a negative 0.48 is a weak negative, but the closer we get to negative 1, the stronger the negative correlation. All right, so here we go. So that correlation coefficient represented by the R is the number represented between 0 and 1. It is going to tell us the strength, how strong, and the direction, positive or negative. But very much important is that R is about the strength of the linear relationship, linearity. It's not about a quadratic relationship or any other polynomial relationship. It is the linearity, measurement of linearity. That's all we're talking about is lines right now. Here's a general guideline of, 0 to zero point 0.3 is pretty weak. 0 to zero point 0.3. But look, 0.45, 0.4, 0.5, 0.6, those are in the middle. 0.4, 0.5, 0.6, that's the moderates. 0.7, 0.8, 0.9, very strong. Strong to very strong. I'd probably even say 0.7, maybe even is moderately strong. Okay. And then, of course, 1 is that perfect relationship. Okay. So the closer R gets to 0, you have a weak correlation. R close to negative 1 or positive 1 is strong. And then, of course, negative R value is negative correlation. Positive R value is positive correlation. All right. And finally, I've already mentioned this, but just to remind you, the correlation coefficient is a measure of linearity. If your data is not linear, you will not describe it with R because that's not an appropriate measurement. R is a measurement of linearity only. So here's this linear relationship, that's fine. Nonlinear relationship, we wouldn't even have an R. Or you know what? The R of this would be close to the 0, even though it may have a quadratic relationship because it's not a linear relationship. Okay, moving on. Back to our problem with the organic foods and the average income. Okay, so here's what that data looked like, and here's what that uh, equation that went through it is. And here is the R value of 0.78. So that's what our R was. So let's kind of talk about these things. If I have got myself an R of 0.78, then here's what we have, direction. I'm going to say it is positive. Okay, I don't think I have really any outliers, and we'll talk about that later. Oh, we're going to describe the relationship with DOFs, DOFS. Instead of socks, it's DOFs. And this is the first time I've attempted to use this mnemonic device, DOFs, because it's direction. If there are outliers, oh, that's interesting. What did that say? Okay. And then if what the form is, linear or nonlinear. And I don't think we really have any outliers. The form is fairly linear. Okay, and then the strength. So probably with a 0.78, I'd say moderately strong. Okay, now I'm going to see how I like DOFs this year because I've always just done it in the past with the song. We would do the correlation coefficient song, and we would do it to the blue suede shoes. There is a strong, there is a weak, positive or negative linear correlation between X and Y. Linear between X and Y. Okay, and the reason that these X's and Y's are in quotation marks is because context, context, context. So here's an example. There is a strong, positive, linear relationship between the amount of hours studied and your grade in statistics. Um, the X and Y order doesn't matter, just those two variables. Okay? There is a strong, there is a weak, positive or negative linear correlation between X and Y. Linear between X and Y. The R. Okay, so if you need to remember that that is the R. Let's do that. Let's write this out for our linear relationship between the average household income and the organic vegetables offered at the local grocery store. Here we go. There's a moderately strong, is a strong, is a weak, moderately strong. Positive or negative? Well, that's positive. Linear, and it is pretty linear. If it's not linear, then we're going to say nonlinear. Correlation between average household income and number of organic products sold. Linear between average household income and number of organic products sold. All right, but your X and your Y in context. Okay, that's our relationship. Now, I think I have a couple other examples. Oh, here's some other graphs. So you can kind of see what the graphs look like with those types of number values that go with them. Here was a strong positive 0.96. Here was a moderately positive 0.67. Here was a weak positive 0.07. I don't even know if I could say there was a positive at all to that. That pretty much just looks like about 0. Here's some negative ones. Negative 0.93. Negative 0.67. Interesting how this negative 0.67 looks about like that one. Negative 0.13. Okay. Oh, you know what? Probably that little one down there in the bottom right probably is what making it look negative. If there wasn't that one down there in the bottom right, I'd probably just see this big blob and think there was no correlation. All right, moving on. Let's practice it. Here we go. So what we have is a graph that is representing the data about price of pumpkin and the diameter in inches. Perfect. We've just had Halloween, or we're about to have Halloween. And so here we go. What do you think's happening with the price of the pumpkin and its diameter? I can tell you because I just went and bought some pumpkins last weekend. The bigger pumpkins cost a lot more. Okay. Now, let's see what we got going on here. The correlation. Okay, let's actually go ahead and put our variables. Okay, what do you think is the response variable? What do you think is the explanatory variable? Okay, so over here, I think the diameter of the pumpkin, the size of the pumpkin is going to be my explanatory variable. And I think the price of the pumpkin is going to be the response. So, my correlation coefficient represented by the R is 0.7, moderately strong. So I think, remember, let's do it. Let's describe it. There is a strong, there is a weak. Positive or negative, linear. Okay, so what are you going to say? There is a strong or what? Or weak? I'm going to say moderately strong. Positive or negative? It's about positive. Linear, yep, it's relationship or correlation. Correlation between price of pumpkin and the diameter in inches. So see, look, there I said Y first and then X. The order doesn't matter. All right. Moderately strong, positive, linear relationship between price of pumpkin and its diameter. Now, this is interesting. Okay. Actually, no, we'll get into that later. Okay. All right. When we get into the coefficient of determination. All right, let's do the next one. Here we go. I have a typo here because it looks like there's a graph farm. Well, it was supposed to be a grape farm. Here's the following graph about the size of a grape farm and the price per pound that it charges its retail clients. So, say if you go to Walmart versus even Sam's, is there a difference in the price per pound? Pretty much. If I buy in bulk, I'm going to get it a little cheaper. Okay, maybe that's going to be the same when the farm is selling it to its retail clients. So let's take a look. I'm labeling first. I'm saying the size of the grape farm is going to be my explanatory variable with the price per pound charged as the response. Negative 0.3. What do you have to say about that? Plus, look at the picture of it. I can tell that it's fairly weak. So, let's do it. There is a strong, there is a weak. What are you going to say? I said weak. There is a weak. Positive or negative? Well, it's negative. Linear. Don't forget that linear. Correlation between size of farm and price per pound that it charges to its retail client. Linear. Between size of farm and price per pound that it charges its retail client. Okay. So while you're finished writing that, then I want to show you this little guide I found. This is not in your notes, but as I was going through some other things before I did this answer key, or while I was doing this answer key, oh, I loved it. And I thought, oh my gosh, I got to show you guys this. So here we go. Take a look. Here is another way to visualize the interpretation of the correlation coefficient. Here is no correlation, no linear correlation here at 0. Then we have a weak correlation, moderate, strong, and very strong, okay? So that's kind of giving you that. And then we go negative side, weak, or moderately strong, strong, negative, and very strong, negative, okay? And then my very most favorite final thing to show you related to this. Look at this. Very interesting. Look at all of these graphs. They all have a correlation coefficient of 0. Well, why? Because look, there is definitely some kind of relationship happening here. I could probably find the circular or the elliptical precalculus function to fit that perfectly. Okay, so there is definitely some kind of relationship happening with all of these data sets. But what did I say? Correlation coefficient measures the strength of linearity. Even though there is some kind of relationship happening here, it's not a linear relationship. Therefore, those correlation coefficients are pretty much 0. All right, there's that. R value, correlation coefficient. Why don't you take a break? Maybe go to your homework right now and fill some of that in. I'm actually gonna go ahead and stop this and do a short little video for the last thing, coefficient of determination. So here we go. Let's go ahead and stop. Let you kind of do a couple of those homework ones before moving on to the last topic.